All right, with so much of discussion about the evolution of oscillator, evolution of amplifier, what has happened in the past, what has happened, what is going to happen in the future, let us now see what is happening in the present in our lab. So, in this module, which hopefully is going to be shorter than usual, we will talk about what is there in the lab, well, inside this box. This is the one box amplifier, the name is Libra HE and it is from Coherent. This is what we have in our lab. Its input, well, I will talk about input later. Its output is 4 millijoule pulses, 800 nanometer modal wavelength at 1 kilohertz. So, this is literally a black box, but fortunately it is a black box whose lids you can take off. So, it is not a black box figuratively. So, if you take the lid off and look from the top, this is what you see. You see that the box actually contains more boxes. The first one is the oscillator. In our case, we have a Vitesse oscillator from Coherent. Now, this once again is a compact titanium sapphire oscillator. In this laser, there are two parts. This side, the side where Vitesse is written, that is where we have this diode pumped solid state laser, which pumps the sapphire laser, which is on this side. And this is a very compact design, pretty much like the Maitai laser from spectrophysics that we had shown when we had visited our lab. This one gives the 80 megahertz output at 800 nanometer, and the pulse energy is nanojoule, right. Then this here is the amplifier. As we know, the amplifier has to be pumped by another laser, typically a Nd:YAG or Nd:ELF laser with some 100-200 nanosecond full width of maximum. This is what it is. This I made a mistake here. The pump laser is Nd:ELF, the name is Evolution from Coherent, but the full width of max is 150 nanosecond in this case, not 250 nanosecond. And this laser operates at 1 kilohertz. That is what determines the repetition rate of the regenerative amplifier. Okay. And then we have also discussed that before the seed can go into the amplifier, it must be stretched. The stretcher is here, and the output of the regen is really a chopped pulse, amplified but chopped pulse. It has to be compressed. This is where the compressor is. So, it is really a very compact design, and that is why in case the alignment goes wrong for some reason, usually it does not. In case it goes wrong, then to get the alignment back is not an easy task. So, schematically this is what happens. The pump laser creates the excited state population in the titanium sapphire crystal inside the amplifier. The output oscillator is stretched, and the stretched seed pulse is fed into it, into the titanium sapphire inside the region. Output of region goes into compressor, and after compression we get the unchopped narrow pulse that we want to work with. Now, this is a schematic, but what we will try to do in the next 10-15 minutes or so is that we will try to get at least a rough idea about the light paths inside this system. Okay. The figures that I have used here are all taken from the user manual of Libra HE. So, this is another way of looking at it. What you saw earlier was really a photograph, this is a schematic. Well, this is what it is. this is the first thing that happens. Was that too fast? Output of the Ti-sapphire laser hits SM1. Now, here the naming is systematic. SM means a mirror in the stretcher. 1 means the mirror that comes first, 2 means the mirror that comes afterwards, and so on and so forth. So, as you see, this one is SM1, this is a SBS. What could SBS be? It is a stretcher beam splitter. In our case, we do not really take the beam out, but here in this laser there is an option. Small amount of the beam can actually come out of this port. So, you can take it out and use it for some other application. The limitation is that you cannot tune it. When it is inside, when the oscillator is used along with a compressor, then it is not a good idea to keep changing the wavelength, because there has to be an exact match between the seed and light within the region. So, comes out, hits SM1, SBS, SM2, and then goes to the stretcher grating like this. Okay. And this here is what the grating looks like. All right. Now, what happens inside the grating? We have discussed it already in a previous module, so we will not repeat. But one thing that we need is, this is the input, comes to the grating, that is what we have shown here using the red light. Can you see what I have drawn here? Can you see these lines? Can you see the red line? Okay. So, the red line comes in, hits the grating, then it hits this big circular concave mirror several times, SM3, goes to SM4, does several round trips, and finally from SM7 the output is obtained, the chopped output. Okay. Where is SM7 here? Do you see? This is SM7, right? So, from SM7, oh, but before that I want to say something. What is this? SPD. S for stretcher. What is PD? No. PD. Polarizer would be only a P. In fact, there is a P here. See, RP, that is region polarizer. But this is SPD. Photodiode. Photodiode. As we have said earlier, it is very important to time the events, right? So, how will you time the events? The way it is done is by using different photodiodes in different places, or by taking synchronous electrical outputs. In this case, what happens is, there is a photodiode, stretcher photodiode SPD, behind the stretcher mirror 4. Okay? And even though these are high reflectors, they are not really 100% reflectors. Even if 99% is reflected and 1% bleeds through, that is enough for the photodiode. So, this photodiode captures the bleed through of SM4, and that output of the photodiode is used for timing the events. All right. Now, let us come back to the light. So, we said that we were at SM7. From SM7, the chopped beam goes to SM8, SM9. It is basically a periscopic arrangement like this. Comes in here, goes up and goes in this direction. Goes where? To SM10. That is the last mirror in the stretcher. From SM10, where does it go? Now, what should happen? Stretching is done, right? What was the red beam now is chopped. Where should it go now? It should go into the region. How does it go into the region? You have seen so many designs now. The first one that we discussed in a lot of detail in one of the previous modules was one where the output of the stretcher went and hit the Ti-sapphire crystal in the region, is not it? And that being at Brewster angle reflected it. So, that is what happens here as well. Okay. So, region goes and hits here. Can you read what is written here? RTS. What is that? Region Ti-sapphire. T for titanium, S for sapphire, R for regenerative amplifier. And then of course, you understand that it will be reflected and it will go into the cavity. Fine, but let us leave that for the moment. I will show you how it goes into the cavity, but before that let us first establish what the path of light is within the region. Okay? Right. So, as you understand, the evolution is the laser that is pumped for the region. What do you have in front of it? This is a mirror, right? What you see here is a mirror, photograph of which is taken from the top. And we are not going to go to the lab and open up the amplifier, because I am a little scared to do that. We do not do it unless it is absolutely necessary. So, this is what we want to do in detail. So, see this what is written here? PM1. And now I think we are getting the hang of the nomenclature. M would be mirror, 1 would be number 1 first. What is P? Pump. That is very simple. So, there is pump mirror 1, the first mirror that the pump beam hits. After that it comes this way actually. Do you see what this is? PL12. So, this is you can, if required, you can increase or decrease the size of the beam. So, it is sort of like a telescope. Okay. You take two lenses of different focal length, okay, and place them side by side, so that their focal focal points match. What will happen? You have this beam, let us say this is where the focus is, the beam gets focused and then it is captured by this lens here. If the focal length of the second lens is smaller, do you agree that the beam will go from a broader waist to a smaller waist? We must say like this, it has been focused here and then it goes out like this. Now, the cross section will be only this much, is not it? So, that is what is there, L1 and 2. Then it comes to PM2, then we have another one PL3, L is length, then PM3, let us go one by one. So, PM1 first hit, then it has gone to PM2, PM1, PM2, then from PM2 it goes through PL3 to PM3. From PM3 it goes straight through the Tisafire rod, and while doing that it goes through one of these mirrors. Since it will get covered, I want you to read the name. What is this? RM3. RM3 is again dichroic mirror. It allows green light to go through, it is going to reflect red light completely. So, it goes straight, okay, then it is dumped. So, pumping of the region is done. Now, let us see what the path of light from the region, well, within the region is. We are not talking about the seed, we are just talking about the region as a self-standing laser. Okay. What is the path? This is the path. So, see PM1, sorry RM1, what is RM1? This one. What do you have after that? PC1, what would PC be? Focal cell, first focal cell, and here you have PC2, the second focal cell. And now we know why we have focal cells in the cavity, to switch in and switch out. This here is a focal cell driver. Focal cell driver means the electronics that okay, tells the focal cell to work or not to work, basically gives the voltage to focal cell. Okay. That is of course not in the focal cell driver, cannot be in the path of the light, it is opaque. Okay. So, from PM1 through the focal cell, and I did not read something, you can read here. What is this? RW, what is that? Yes, a region wave plate. So, you can turn the polarization as required. So, from RM1 it goes to RM2, from RM2 it goes to RM3, remember that was RM3, and when it goes through RM3, then RM2 to RM3 is through the TISAF. Now, if you look carefully, do you see the crossover? Yeah, crossover between the green light and the yellow light, because the pump cannot be coaxial with the cavity, then it can be a problem perhaps. So, a little bit of angle is there. So, it crosses, it goes to PM3, then from PM3 it goes to PM4. No, what am I saying? RM. From RM3 region, R for region, P is for pump. From RM2 it goes to RM3 through the Tisafire crystal, And by the way, the tisophyre crystal is at an angle, so we will come to that later. Then from RM3, what is there after this? What is RP? I told you, region polarizer. So, it goes through the region polarizer, through the focal cell, the second focal cell to RM4. Okay. From RM4, it goes to RM5, right. So, now it looks like a W kind of thing. Soon the W will no longer be W, it will be something more than W, triple U, quadruple U, something like that. Okay. From RM5, it goes to RM6, and that is the end of the cavity, region cavity. Okay. Is the cavity now defined. RM1 to RM6 folded several times, and the light passes through different optical elements. It has to pass through the gain medium, of course, but it also passes through this focal cell, half wave plate, polarizer. Okay. And the polarizer that is there is also at an angle, that becomes important a little later. Now, before going further, now can you guess where the seed goes? The seed has come from SM10 and it has hit the region tisophyre crystal. From there, where will it go? To help you, I can put it like this. This is how the tisophyre is, and the seed comes like this. In which direction will it go? Definitely something like this. So, what happens is, there is another bleed through and there is a region photodiode as well, you see RPD. So, that is the most important thing, that is what you see on the oscilloscope. But now coming back to the original discussion. So, this is where, did you see? The seed goes from the tisophyre crystal to RM2, all right. And then here alignment becomes very, very important, because the path from the tisophyre laser RTS to RM2 has to be exactly coincidental, exactly the same as the path of the self sustaining beam inside the laser. Otherwise, it will not be able to do the round trip. Are you clear? Yeah. So, the self sustaining laser, the yellow lines that we have drawn, that sort of defines the path, and your seed, sharp seed, must travel back and forth along that path. That is how it does the round trips. So, it is essentially the same thing that we had discussed earlier, the same figure that is there in the laser spectroscopy book. The difference is there, for simplicity's sake, a straight cavity was shown. Here the cavity is folded, because if you fold the cavity you save a lot of space. Are you clear? Any question? Can I go ahead? Great. So, one thing that I was taken a little unaware of, because I forgot about it, is this: through the RM4 mirror there is a bleed. Bleed means 0.5%, 1% of light getting through the mirror. That is enough. It is captured by this RPD, the photodiode inside the region cavity, and we see the output. We are going to discuss what we see. All right. Now, it is doing round trips. Now, you want to switch it out. How will you do it? Focal cell 1 has switched it in, and we know the sequence of events, switched it in, turned off or whatever, or not turned off in this case. Now, if you want to switch it out, then focal cell 2 has to go on, and then from where will it get reflected? What is the polarizing optic after focal cell 2? Look at the yellow line. This is focal cell 2. It comes here. While coming back, PC2 gets turned on, or maybe while going, PC2 gets turned on, 45 degrees rotation, coming back 45 degree rotation, comes straight where? Region polarizer. So, this polarizer is actually at a 45 degree angle, or well, not 45, some angle. Polarizer is not like, so this is the direction of the beam. Polarizer is not like this, it is like this. right. So, as long as the polarization of the light is such that it will go through, there is no problem. Sorry, it is like this. The moment you turn the polarization by 90 degrees, it will now go off like this. Clear? So, this is what happens. From region polarizer, it goes to, what is this called? Region mirror 7. Okay. It is still called region mirror, it has not gone into the amplifier, sorry, compressor yet. Then it goes to region mirror 8, 9. See, what happens is, the heights may not be matched. The height at which the optics are, well, in stretcher and in the compressor and in the region, they might be different. So, when you want to change height, I think now we are familiar with it, we have to use something like a periscopic arrangement, right. So, it goes to these mirrors and then it hits CM1. What is CM1? Compressor mirror 1. Now, the compressor starts, and we have already discussed what happens inside the compressor. It gets compressed, the amplified charge beam, and it goes out. In our case, it goes out in this direction. In some cases, if you want the light to go out from here, you need to have another mirror here. See CM6? We do not use CM6, it is not in place. So, if CM6 is there, then the light would go out in this direction. It all depends on how you want your experiment to be. Okay. In our case, it comes out of this port, and that is your 1 kilohertz amplified 4 millijoule unchapped 70 femtosecond beam. All right. Now, if you look at the as we have said earlier also, it is not just about light, it has got a lot to do with electronics, time electronics to be more precise. And you have seen that we use photodiodes to monitor the beam in different places of this contraption, right, and outputs are all here. Okay. From here, you have to use the signals appropriately to give delays that are required to sustain the amplified operation. So, we have discussed this once already, but still let us look at the figure that is there in the user's manual. To start with, can you read whatever is written here? I just copy pasted from the manual. Okay. So, first of all, you have something like that looks like a comb, right. That is your output of the oscillator, 80 megahertz. So, the pulses are very, very close. Next, what happens is you pump the amplifier, right. This is the laser pulse of the pump laser, 150 nanosecond. So, what you want to do really is that you want to wait until this time, because in this region more or less the intensity of pump is same. In fact, I will go one step further and I will show you the gain. As we discussed in one of the previous modules, the gain trails a little bit, right, and persists a little longer as well. See, in this region it is not horizontal, of course, but the change in gain is not so much. This is the region where you want to do the amplification. This is the time regime in which you want to do the amplification. So, what you do is you introduce this delay 1. Look at the output of the laser, you will see this delay 1, delay 2 and all that. This is delay 1, right. So, now well, we do not have to go into coarse delay, fine delay and all that. This is where the amplification begins. So, delay 1 is given to start amplification, delay 2 is given to switch the pulse out, right. And then this is what we had discussed earlier. Do you see, this is what you see on the oscilloscope, do not you? Build up of the region, the seed being amplified in the region, and then more or less near the maximum you switch it out and then you do not see the remaining part. And this is the pulse that is switched out. Okay. That concludes our discussion of oscillators and amplifiers. It has been quite a long journey, but I hope that now the black box is no longer so black to us, at least it has become a gray box. Okay. We still do not want to play around and change things inside, but even when we operate, unless we know what is the meaning of this delay 1, delay 2 is, we can make mistakes. So, it is important to know what is going on here. So, what I will, of course, not for the remote audience, but for in-house people, I recommend that you read the manual and follow up on this. You do not have to read everything, because we do not really do everything. We do not install the grating and all every day, but you should know what is what, you should know the sequence of events, you should understand how it is working. Okay. We stop here today. In the next module, we hope to talk about the next step. The amplifier gives you a single wavelength, 800 nanometer in this case. Of course, it has its own bandwidth, but it is not tunable. If I want tunability, then I want to use something called an optical parametric amplifier. The problem of discussing optical parametric amplification is that it is a nonlinear optical process. So, ideally, we should talk about it only after we have performed a significant discussion of nonlinear optics. But there are two problems to that. First of all, I am not really a nonlinear optics person. Secondly, to do a thorough discussion of nonlinear optics, that would require a long time. So, we will see what we will do. Perhaps we will discuss nonlinear optics without derivation, only the functional parts that we need, and we will see whether we can go ahead and talk about optical parametric amplification. As we will see, most of the time we want to do collinear amplification, but then for some applications it is better to have a non-collinear amplification. So, you do not want to use an OPA as such, you want to use what is called a NOPA, non-linear OPA. So, in the next 2 or 3 modules, we hope that we are going to talk about OPA first with reference to the TOPAS system that we have in our lab. And then what I really want to do is, there is this nice discussion of NOPA in a review written by, not a review, they had built one by Professor Umapati in Current Science few years ago. Maybe we will try and discuss that. Okay. So, here we close the discussion on amplifiers.